Hey there, and welcome to this explainer. I'm your friendly tutor, and today we are going to absolutely crush your upcoming calculus exam. We're going to do this by tracking a physical object through the dynamic, kind of mind-bending world of vectors and matrices. If you've ever found yourself struggling to visualize how all that math on your page actually translates to real physical movement in the real world, well, you are exactly in the right place. Let's get into it.
Here is our game plan for today's review session. We'll be hitting vectors and physical motion, adding and scaling vectors, dot and cross products, determinants, intersections and planar equations, and then we'll wrap it all up with the ultimate vector toolkit.
All right, part 1, vectors and physical motion. To begin this hero's journey of a single point moving through space, we first need to get really clear on what exactly is moving and how we measure it.
Now you might be wondering, what's the fundamental difference here? Well, think of a scalar as just an amount, a quantity with magnitude only. Things like the mass of an object, the temperature in your room, or just raw speed. But a vector is a whole different beast. It's an actual arrow that gives us magnitude and direction. It tells us not just how fast our object is moving, but exactly in which direction it's traveling. We're talking about forces, velocity, and physical displacement.
And we have a standard way of tracking this movement using our basis vectors, I hat, j hat, and k hat. Now these are unit vectors, which means they have a precise length of exactly 1, and they point directly down the x, y, and z axes. You can really think of them as our fundamental building blocks. They're like the primary colors of our coordinate system, allowing us to stretch and precisely track motion anywhere along a 3D grid.
Moving right along to section 2, adding and scaling vectors. Let's see what happens when we start throwing multiple forces at our moving object.
So picture this. What actually happens when two completely different physical forces collide in 3D space? Imagine an animated object being pushed hard in two totally different directions at the exact same time. Finding its true final path requires a little something called vector addition.
The really cool thing here is that there are multiple ways to figure this out, but they all give you the exact same physical reality. Visually, you can slide the arrows tip to tail to form a triangle, where your net displacement simply connects the start to the finish. Or you can stick them tail to build a parallelogram and just draw a line right down the diagonal. But honestly, algebraically, it's even easier. You just take the matching x, y, and z components and add them right up. Whether you draw it out or crunch the numbers, you are finding the exact same final destination. Now don't let the formal terminology freak you out. Scalar multiplication is incredibly intuitive. It basically just means multiplying our vector arrow by a regular, everyday number. Multiply by 2, you literally just stretch the arrow out to be twice as long. But, and here is a huge trick for your exam, throwing a negative sign in front just takes our moving object and spins it entirely around, exactly 180 degrees right into the opposite direction. Okay, deep breath. We are now entering heavy exam territory, section 3, dot and cross products. These are the two special ways we multiply vectors to compute physical interactions. I see students mix these up all the time, so let's get this crystal clear. The dot product, sometimes called the scalar product, just leaves you with a single flat number. It simply measures how much one vector overlaps or projects parallel onto another. But the cross product? That's entirely different. It creates a brand new physical 3D arrow that juts straight out into space, perfectly perpendicular to both of your original vectors.
So how do you know where that new cross-product arrow is actually pointing? We use the right-hand rule. If you physically take your right hand, point your fingers straight along the first vector, A, and then curl them toward the second vector, B, your thumb naturally points in the exact direction of the cross product. And honestly, this brilliantly illustrates why order is absolutely crucial. If you try to reverse it, curling from B back to A, you physically have to flip your whole hand upside down. So A cross B points in the exact opposite direction of B cross A. Order is everything.
Awesome. Let's transition to section 4, determinants and scaling 3D space. We're shifting our perspective here from single arrows to massive matrices that actually transform the physical space around us.
Instead of just blindly memorizing a formula for this, I want you to picture an animated, vibrant grid stretching out in front of you. A matrix physically stretches and transforms that grid. The determinant simply tells us the precise mathematical factor by which the volume of that grid just expanded or shrank. For instance, if a basic 1 by 1 by 1 cube gets stretched into a 3D shape, which we mathematically call a parallelepiped, and its new volume is 6, your determinant is exactly 6.
But what does the actual sign of that number tell us? Well, a positive determinant means perfectly normal scaling.
But a negative determinant, that means our whole 3D right-hand orientation just flipped inside out into a left-handed reality, kind of like stepping into a mirror. And a zero determinant, that is a big one. That means our entire 3D volume got catastrophically squished down into a flat plane, a single line, or even a single dot. The volume is completely gone.
Now, when you are actually crunching the algebra for a 3x3 determinant on test day, you'll use a step-by-step method. You pick an entry on the top row, meticulously cross out its entire row and column, and then multiply that entry by the smaller 2x2 matrix that's left over. But listen to me carefully. Whatever you do, do not forget to alternate your signs for that top row. Positive, negative, positive. Missing that middle negative sign is literally the most common pitfall I see on exams. All right, Section 5, Intersections in Planar Equations. Let's take this entire tool belt we've built and apply it to some complex 3D geometry. Say you want to mathematically build a flat plane floating infinitely in 3D space. Here is your recipe. First, you need a starting position vector, just an arrow pointing from the origin to any random spot on your plane. Then, you need two completely different directional arrows that lie flat on that surface. By multiplying those two directional vectors by variable scalars, usually called t and s, you can literally travel anywhere on that infinite flat surface. But what if we have two lines flying through this 3D space? Do they crash? To find out, you set their parametric x, y, and z equations equal to each other. You solve for those scalars, s and t, using two of the equations, and then plug them back into the third to check your work. And this is a wild reality of 3D math. Unlike drawing on a flat piece of paper where lines almost always cross, two lines in 3D space can completely miss each other. If your final coordinates don't perfectly match up in that last step, the lines are what we call skewed. They just fly right past each other.
We've finally reached the grand finale, Section 6, the Ultimate Vector Toolkit. Let's bring all 10 of these concepts together. This right here is absolute gold. It consolidates everything. All those complex algebraic formulas we've mapped to physical motion, finding magnitude, computing the dot and cross products, and crunching those determinants. They are all neatly organized right here. This is your ultimate quick reference sheet. It's the toolkit you need to confidently translate algebra right back into geometric motion. As you head into your exam armed with these amazing tools, I want to leave you with this final thought to ponder. If simply tweaking the numbers in a matrix can reverse orientation, alter physical displacement, and even squish the very volume of our geometric space down to absolute zero, what other hidden dimensions of reality are out there, just waiting for you to discover the right equation?
Hey everyone, welcome to this calming study guide explainer. Look, if you're feeling a bit anxious about your upcoming calculus test, I just want you to take a deep breath. Right now, you're in exactly the right place. Today, think of me as your personal tutor. We're going to break down these calculus derivatives into totally manageable, bite-sized pieces. We're not going to rush. We're just going to look at the brilliant logic behind the math so you can walk into that exam room feeling absolutely confident.
Here's our roadmap for this review. We'll start with origins and tangent lines, move into basic derivative rules, then tackle complex rules and errors. After that, we'll look at acceleration and turning points, do some rational and radical practice, and wrap up with an exam checklist and formulas. Let's dive in. Section 1. Origins and tangent lines. Why calculus actually exists.
You know, it's actually incredibly comforting to remember that even historical geniuses like Isaac Newton and Gottfried Leibniz were once just sitting there staring at blank pages, totally frustrated. Back in the 1600s, traditional algebra was completely failing them when it came to handling constantly changing speeds. So in the 1660s, Newton literally had to invent these tools from scratch just to calculate the instantaneous velocity for falling bodies and planets moving through space. Then, a few years later, Leibniz independently created the foundational calculus notation that we're still using today. They built this math out of pure necessity to solve real-world problems.
And this perfectly illustrates what they were trying to solve. Visually, just remember that a derivative simply helps us find the exact slope of a tangent line hitting just one single instant point on a curve. That's your instantaneous rate of change. Now contrast that with the secant line you see on the left. That bridges two separate points to give you a broad, average rate of change. Calculus is all about zeroing in on that single, precise instant.
Section 2. Basic Derivative Rules. Building your mathematical toolkit.
All right, these three rules are your absolute foundation. First up, the constant rule. The derivative of any isolated number, like 5 or -7, is just 0. Why?
because a constant literally never changes. Second, the power rule. A great trick here is to just remember times and take. You multiply the exponent to the front, and then you take 1 away from the power. Simple as that. Finally, the constant multiple rule. If a number is attached to an x, you just keep it hanging out in front and multiply it by your derivative. If you have these 3 down, you've already got the basic foundation to completely ace this.
Section 3. Complex Rules and Errors. Navigating the Heavy Lifters. Okay, take a slow, deep breath here, because we're gently moving to the slightly heavier formulas. But I promise, you are fully capable of handling them.
First up is the product rule. When 2 distinct functions are multiplied together, like x squared times the sine of x, you can't just multiply their derivatives. No way. Instead, simply differentiate the first part while leaving the second one alone, then add that to the first part left alone, multiplied by the derivative of the second.
Now for fractions, we use the quotient rule, the classic memory trick. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. But pay close attention to that crucial subtraction sign in the numerator. A super common mistake students make under pressure is mixing up the order of the numerator and getting that sign wrong. Just remember, always start with the bottom function first.
Finally, the chain rule. If you spot a nested function, like a whole expression inside parentheses raised to a massive power, the chain rule is your go-to. You take the derivative of the outside function, keeping the inside exactly the same. But, and here is where students often lose points, please do not make the common error of forgetting to then multiply all of that by the derivative of that inner function. That inner derivative is absolutely crucial. When you sit down for the actual exam, I want you to rely on these friendly little heuristics to keep that test anxiety at bay. Basically, let the visual structure of the equation tell you which rule to use. Look for nested parentheses to trigger the chain rule. Spot multiplied x terms? That's the product rule. See a top and bottom fraction? Boom, quotient rule. Always double-check your negative signs, and most importantly, just take your time. Do it one piece at a time.
Section 4. Acceleration and Turning Points. Connecting abstract math to physical reality.
Let's step back and think about a falling object. Galileo observed its position over time, which gives us our first position function. Now, by taking the first derivative of that position, just using our simple power rule, we find its velocity at any exact instant. And watch how beautifully this builds. If we take the second derivative, meaning the derivative of the velocity, it perfectly reveals the constant acceleration of Earth's gravity at exactly 9.8 meters per second squared. It's like unlocking the code of the universe. Furthermore, derivatives are absolutely brilliant for graphing. If you ever need to find the absolute highest or lowest turning points on a graphed curve, all you have to do is set your derivative to 0 and solve. Why? Because the slope of 0 means the tangent line is resting perfectly flat. It tells you exactly where the graph stops going up, takes a breath, and starts going down.
Section 5. Rational and Radical Practice. A step-by-step guided walkthrough.
Okay, take a moment to look at how we find the derivatives of fractions and roots here. Before you even try to differentiate them, think about how you would rewrite them. Trust me, proper preparation makes the calculus so much easier. Let's look at the rational function first. Don't panic when you see an x trapped in the denominator. You can easily rewrite it by just moving that x to the top, which makes the exponent a -2. Simple algebra, right? Now just apply your standard power rule. The -2 comes to the front and the exponent drops to -3. Finally, just drop that x variable back down to the bottom to finalize your clean answer as -2 over x cubed.
Radical functions follow that exact same logic. Just rewrite the square root as a fractional exponent, so it becomes x to the 1/2 power. Use your trusty standard power rule to get 1/2 x to the -1/2, and then carefully convert it back into a clean radical expression. For the cube root of x to the 5th, remember the root is the denominator and the power is the numerator, so it becomes x to the 5/3. Apply the power rule, and you are totally done.
Section 6. Exam Checklist and Formulas. The finish line. You're definitely going to need to commit these 6 essential trigonometric derivatives to memory. But I want you to notice a really helpful pattern here. Every co-function, cosine, cosecant, cotangent, always results in a negative derivative. Memorizing that single pattern is a total game changer and will save you from making those frustratingly simple sign errors on test day.
So take a look over this rapid review checklist and just trust in the rules you've learned. Remember that taking your time to breathe and algebraically prepare the function beforehand prevents so many silly errors. Let the visual structure of the problem trigger the correct rule in your mind. You know exactly how to handle multiplied terms, you know how to handle fractions, and you definitely know what to do with nested parentheses. I want you to always remember this idea. Understanding the concept first makes the formulas obvious. They stop feeling like arbitrary rules and start feeling like logical consequences. These formulas aren't just arbitrary, confusing symbols meant to torture you. They are brilliant, logical tools carefully designed to decipher the changing world around us. Once you truly get why they exist, applying them is just a natural, logical consequence. All right, you are fully prepared to calmly and confidently conquer this exam. But beyond getting a great grade, just know that these exact derivative rules quietly run the technology in your pocket. From mapping your GPS route, to training artificial intelligence, to calculating life-saving medical dosing. So, once you ace this exam, what amazing future problems are you going to solve with these tools next?
Welcome back, everyone. Listen, I know why you're here. In this explainer, we're going to finally calm that frustration you might be feeling and get right down to the core logic of calculus. We are doing this before we tackle any crazy formulas, okay? Look, you were probably taught that math just naturally builds on itself. Numbers, then algebra, then geometry. And honestly, for most of us, that works perfectly fine. But calculus, man, that's where so many students who are usually great at math suddenly hit a brick wall and feel totally lost. Let me tell you, it's not because you aren't smart enough. No way. It's literally just because nobody took the time to explain what calculus actually is before throwing a bunch of complicated equations on the whiteboard. So, let's take a deep breath. Today, we're acting like a one-on-one tutoring session. We are strictly focusing on the pure ideas. Okay, so let's dive right into this super relatable question. If your phone battery is at 40%, is it going to last 2 hours or like 20 minutes? Static numbers alone literally can't tell you how fast that battery is draining. Same thing with your car. Static math doesn't know how your speed fluctuates in heavy traffic. See, regular math, the kind we all learned in elementary and high school, is absolutely fantastic at handling things that stay exactly the same. If you drive at a rock-steady 60 miles per hour for 2 hours, boom, basic multiplication tells you the distance is 120 miles. But what if your speed changed the whole time? What if you sped up to pass someone, hit the brakes in traffic, and stopped at a bunch of red lights? Well, basic math kind of completely falls apart there. It cannot give you an exact answer for that. So the absolutely crucial takeaway here is this. Basic math is great for the static stuff, but calculus? Calculus was built specifically to solve problems in a world that is constantly, relentlessly changing. And let's face it, that's the real world, right? Prices change, speeds change, temperatures change. Calculus gives us the exact mathematical engine to handle those real-time fluctuations. Actually, everything in calculus pretty much boils down to two core questions. 1, how fast is something changing right now? And 2, how much has something changed in total? That's the whole shebang.
To help you digest all of this without feeling overwhelmed, here is our game plan for today. 1, the math of change. 2, the historical breakthrough. 3, definite versus indefinite integrals. 4, evaluating basic integrals. And finally, 5, integration by substitution. We'll take mental breaks as we go, so don't worry.
All right, let's hit section 1, the math of change. We're going to understand limits, derivatives, and integrals. Let's step onto the first rung of the ladder here and establish the absolute foundation of all calculus, the limit. Imagine you open up Google Maps on your phone, right? You find a highly curved, super winding road. Now, I want you to imagine zooming in on that curve. You keep zooming, zooming, zooming infinitely close, until suddenly that curve appears as a perfectly straight line on your screen. That brilliant visual describes the limit. It tells you the exact value you are heading toward as you get closer and closer to a microscopic point. Because sometimes in math you simply cannot calculate the exact value right at a specific point, but you can get infinitely close to it. A limit tells you what value you are approaching. This is absolutely crucial to grasp. A limit is not about where something currently is, it's all about where something is heading. That tiny little shift in perspective, that's the foundation for literally everything else we're about to do.
And that brings us straight to our two main tools, the derivative and the integral. Let's really picture this. Imagine watching a dashcam video of a car and then hitting pause. The derivative calculates the precise, instantaneous rate of change right in that frozen frame. Not the average speed over the last minute, but the exact speed right then. On the flip side, the integral answers the question how much in total. Think about a rainstorm. It drizzles, then it pours heavily, then it goes back to a drizzle. You can't just multiply the time by one average rainfall rate, right? It wouldn't be accurate. The integral steps in and calculates the total accumulation by adding up an infinite number of tiny, constantly changing pieces. Visually speaking, if you look at a curve drawn on a graph, the integral is calculating the total area completely trapped underneath that curve, built up moment by moment.
Moving right along to Section 2, the historical breakthrough. Let's see how we connect these two halves of calculus.
So, how did we actually figure this all out? It's an incredible story of mathematical discovery. For literally centuries, dating all the way back to the ancient era, the Greeks used this really intuitive method, the method of exhaustion. They basically realized, hey, if we can't measure the area of a weird curved shape, let's just pack it full of tiny rectangles. Because finding the area of a rectangle is easy, it's just base times height. The more rectangles you squeeze in there, and the thinner they get, the more accurate your area becomes. Fast forward a bit to the early 17th century, and Gottfried Wilhelm Leibniz introduces the integral symbol we use today. You've probably seen it. It looks like a really tall, elongated letter S. And there's a cool reason for that. It literally stands for a limit of sums of those infinite tiny rectangles. But the real magic happened in the late 17th century, when Isaac Newton and Leibniz mathematically unified these concepts.
This unification was a massive, game-changing realization that became known as the fundamental theorem of calculus. What it proves is that differentiation, finding a rate of change, and integration, finding total accumulation, aren't just two random separate tools. They are exact inverse operations. Newton and Leibniz independently figured out that finding the slope of a curve and finding the area under a curve are two sides of the exact same mathematical coin. I mean, talk about a light bulb moment.
A great way to think about this inverse relationship is to picture moving up and down a ladder. Taking a derivative basically moves you down a rung, and integrating that exact same function, well, that moves you right back up to where you started. It perfectly undoes it. It's exactly like how addition undoes subtraction or multiplication undoes division. For example, if you have an equation that maps exactly where your car is, taking the derivative gives you a new equation for your car's speed. If you take that speed equation and integrate it, boom, you go right back up the ladder to your original position equation. Differential and integral calculus are just beautifully locked together into one cohesive system.
Okay, take a quick breath. That was the why. Now let's move to Section 3, definite versus indefinite integrals, where we transition from these cool concepts into actual algebraic notation.
When you actually sit down to evaluate these equations, you absolutely must distinguish between definite and indefinite integrals. A definite integral has a specific starting point and a stopping point. We call those the limits of integration, and they're written right on the top and bottom of that tall S symbol. Because you're evaluating over a very specific interval, your final answer is going to be a concrete, specific number, like the exact square footage of an area under a curve. But an indefinite integral, it has no limits written on it at all. Instead of looking for a number, you're looking for a general family of functions. You're looking for the antiderivative itself.
Now this leads us to the most infamous trap in calculus, the plus c. Because the derivative of any constant number is simply 0, whenever you solve an indefinite integral, you absolutely must add the constant of integration, plus c. Why? Well, think about it. If you take the derivative of x squared plus 5, you get 2x. The 5 just disappears. If you take the derivative of x squared plus a million, you still just get 2x. So when you're running the process in reverse and you integrate 2x, you know the main part is x squared. But you have no earthly idea what that original hidden number was. It could literally be 1, 10, or a billion. So we just write plus c to cover our bases. Don't forget it on your exams. Before we tackle our first real problem, I want you to mentally bookmark this cheat sheet of integration properties. Just like derivatives, integrals have rules that let us break down scary-looking problems into manageable chunks. If you have a constant number multiplying your function, you can literally just pull it completely outside of the integral symbol so it doesn't clutter up your math. If you've got an equation with sums or differences, like two functions added or subtracted, you can just split the whole thing into two completely separate, super easy integrals. Committing these simple rules to memory will make the complicated algebra feel way less intimidating. All right, let's put this into practice. Section 4. Evaluating basic integrals. Let's look at the rules of the game in action.
Since we know integration is simply taking an antiderivative, finding your answer is honestly as easy as taking the familiar power rule you already learned for derivatives and running the tape completely in reverse. Remember how taking a derivative meant multiplying by the exponent and then dropping that exponent down by 1? Well, to do the exact opposite, step 1, you start with your term. Step 2, you increase the exponent by 1. Step 3, you divide the entire resulting term by that brand new exponent. So the integral of x squared becomes x to the power of 3 divided by 3. And step 4, of course, because we're smart and we remember, we instantly tack on our plus c.
And hey, this precise reverse logic applies to trigonometry and special functions too, which is great news because it means if you already know that the derivative of sine is cosine, then you automatically know the integral of cosine is sine. You're literally just reading your derivative flashcards backward. Same with exponentials. The derivative of e to the power of x is famously just e to the power of x, so naturally its integral is the exact same thing. Now there is one sneaky exception you got to watch out for, and that's 1 divided by x. You can't use the reverse power rule there, because subtracting from that exponent gives you a 0 and dividing by 0 is mathematically illegal. So the integral of 1 over x uniquely becomes the natural logarithm of x plus c.
Okay, let's take one more deep breath before we hit our final topic. Section 5, Integration by Substitution. This is how we systematically conquer those advanced exam problems.
Sometimes you're going to look at a problem on a test and realize none of your basic rules apply. It's just a terrifying, tangled web of functions stuffed inside of other functions. When an integrand looks like a total mess, we apply the substitution rule. Most people just call it U substitution. It essentially acts like the chain rule, but in reverse to drastically simplify the equation. Here's the playbook. You isolate the ugliest, most complex inner part of the function, and you just label it U. Then, you differentiate U to find du. Substitute those simple letters directly into your original, messy integral, and suddenly the entire complex equation collapses into something incredibly basic that you can integrate in your sleep. Then at the very end, you just revert the u back to the original x variables.
Let's actually walk through this step by step so you can see how beautifully it works. Let's say we need the integral of 2x times the cosine of x squared plus 1. Panic-inducing, right? But wait, let's make u equal that annoying inner function, x squared plus 1. Now, step 2, we take the derivative of that u, which gives us du equals 2x dx. Now look back at the original problem. We literally have a 2x and a dx just sitting right there. So step 3, we substitute. We swap it all out, and suddenly our nightmare problem is just asking for the basic integral of cosine of u du. Step 4, we integrate that to get sine of u plus c. And step 5, we just swap the original x squared plus 1 back in for u. Boom! Your final answer is sine of x squared plus 1 plus c. You just transformed an advanced calculus problem into a totally solvable puzzle just by keeping your workspace organized.
Ultimately, what I want you to walk away with today is this. These aren't just arbitrary, boring procedures to memorize for a test. They are the exact mathematical tools used to decode a constantly changing world. Calculus isn't some dusty textbook theory. When your phone's GPS figures out exactly how far you've traveled based on your constantly fluctuating driving speed, it is performing an integral. When artificial intelligence trains itself and adjusts its machine learning models, it is running millions and millions of derivatives. Calculus is literally the engine running silently in the background of almost all modern technology. You now understand the profound mathematical language of change. So knowing that calculus powers everything from tracking a delivery to training AI, what hidden everyday changes will you calculate next?